where we were yesterday. Does anyone have any questions about anything from yesterday before I begin? All right, so just to kind of give a quick review what we're doing, we're talking about energy. And what is energy exactly? It's the capacity to do work. So we define work as the force times the displacement times the angle, the cosine of the angle between the force and the displacement. So just to be clear, the delta x does not have to be in the x direction. It could be in the y direction or any direction. It's just the generic displacement, and the force is the generic force. So that could be the force of friction. It could be, some applied force, the force of gravity, the normal force, tension, whatever. But in practice, we are operating with the work energy theorem, which says the net work equals the change in kinetic energy. And last time we did a trick where we said we're going to split the work into the work done by gravity plus the net work done by all other forces. And then we take the work done by gravity and we move it to the other side. So we say the net work done by other forces equals delta Ke, and technically it would be minus the work done by gravity, but we redefine that and call that the change in potential energy. So philosophically, what we're doing is we're treating the work that gravity will do. So if I lift something up above the ground, so that if I release it, gravity will do work on it. We treat it as if it has that energy already, and we call that energy potential energy. So textbooks and physics classes tend to get a little sloppy and not all write other forces. We just, at some point, we sweep that under the rug and we forget about it, and we say net force equals delta Ke plus net work equals delta Ke plus delta Pe. And we just have to remember in the back of our mind that we've all made this agreement that when we're talking about work, we pretend that gravity doesn't do work because we're already counting it over here. And so we just don't want to count it on the left-hand side too. So when are we going to have work on the left-hand side? So in practice, every force but gravity should be considered, or I guess in theory, every force but gravity should be considered over here. But in practice, really the only two cases where there's going to be net work is going to be either there's applied force. The problem says, Joe pushes the box, okay, with this force at this angle. Then Joe's doing work. Or when there's friction. And that's probably number one. When we see friction, that means there's going to be work on the left-hand side. And when there's not friction, unless we are specifically told about somebody doing work, then there's going to be no work. So you'll see as you're doing homework, probably half of the problems or more have no work. The examples we did yesterday with an object flying off of a cliff, and that had only gravity working, so there's no work being done. The same goes for the box sliding down the ramp unless there's friction, things like that. So our kinetic energy formula is 1/2 mv squared, and our potential energy formula is m times g times y, or we could say m times g times h. And we have the same freedom here in determining what we mean by y that we had in kinematics. So we measure a place, we call that the origin, and then if we're above that place, that would be a positive y. If we're below that place, it's going to be a negative y. And so we have the same freedom to decide where that is. So in practice, what I would recommend is we just take the lowest point in our problem and we call that y equals 0. Then everything is measured sort of from that lowest possible point. But there's not a deep meaning to saying I have so many joules of potential energy, because that really just means sort of how high I am above the place I called 0. What matters is when the potential energy changes. That's something, it doesn't matter if I call, for example, I'm in the basement right now. So if I call the floor of this room 0, but someone up stairs, they might call the floor of this room minus 8 feet or something. When I do an experiment, it doesn't matter, because if something drops 2 feet and it goes from 2 feet down to 0 or -6 down to -8, it's still dropping 2 feet, and that's what we can measure. So this is basically an overview of what we had talked about yesterday. Today we are planned to really just solve problems from the book, and we're going to learn about one new kind of energy in the second half of today. Any questions now that I've reviewed and you see, kind of remember what we were talking about? Does anyone have questions about any of this? Okay, so let's get started with a textbook practice problem. So I'm in the 3000 Problems book, and I'm looking at problem 7.67. So this says that a simple pendulum is released. Find the speed as it passes through point C in the picture. So the picture has a pendulum, and it's actually released from up here. This is point A, and there's a 75 centimeter length of the pendulum. And basically, this is point B, and it swings down to point C. We want to find the speed when it gets down there. So we start, as we will always start, with network equals change in the energy. And now, instead of saying change in KE, I'm just calling this change in energy because we recognize maybe there's different kinds of energy now. So this really becomes delta KE plus delta PE. And that's equal to the net work. So the next thing I have to do is I have to figure out, you know, do I have any work or not? So we'll get that by drawing in our forces. We have the force of gravity, we've got red. And then we have some tension here. And what we want to know is, do either of these do work? So with gravity, technically it does work, but what we do, we kind of wink at each other and say, no, it doesn't do work. Because why? Because we're using the potential energy concept. How about the tension? So the tension, it could do work. It does work on an elevator when it lifts the elevator up. What about now? Well, so what we have to do is we have to see that the tension is really making kind of a right angle to the velocity, which is the direction that it's moving momentarily. So because the tension makes a right angle to the motion at every instant, it doesn't do any work. So, you know, as I said, the practical rule is if there's no friction, very likely there's going to be no work. Okay, so then we have 0 on the left. That's good. But if we didn't have 0 on the left, no problem. It means we have to compute some number on the left that's not 0. But it's generally not a big issue. It's just one extra complication. Then we're going to have the delta KE. It kind of splits open into KE final minus KE initial. And the delta PE splits into PE final minus PE initial. And there's a plus sign in between because we're adding delta KE and delta PE. So that's what happens when I open up those deltas. I open them up and I see, you know, each one has 2 terms. And then I have to go through those terms one by one. Will there be final kinetic energy? Well, the final location is point C. It's going to still be moving at point C. So we will have final kinetic energy. Is there initial kinetic energy? Well, we have to read in the text again and make sure, because I didn't translate it into math. It says it is released from point A. So when something is released, that implies that it's not thrown or shot or something. It's just let go of. So that mathematically we would say released means V initial equals 0. And that means I can cancel out the initial kinetic energy. So how about the potential energy? How do I know if I have that? Well, I can't really say if I have that until I decide where y equals 0 is. So let's just say that the bottom is y equals 0. I mean, I can pick any point I want and it will not affect the work. So I pick a point that makes it easy for me. And in this case, if I pick the bottom to be y equals 0, then I can say there's no final potential energy because it's gone down to height 0. But then there must have been initial potential energy because I'm not at 0 at the beginning. Okay, and that's it. If I would pick the top, point A, to be y equals 0, I will get the same exact numerical answer. If you don't believe me, try that out on your own and you'll see how it works. So if I now open up the kinetic energy final and potential energy initial and put the formulas, notice I haven't actually done any math yet. We're just doing logic. We're just thinking through the logical process. And even replacing KE final with the formula, that's not really math yet. I'm just rewriting it with a different formula. So we get 1/2 mv final squared minus m times g times y initial. So always the kinetic energy formula is 1/2 mv squared, but I may have m1 or m2 or v initial or v final depending on what's going on in the problem. Same thing for potential energy. It's always m times g times either y or h. You can use whichever variable you like. The books are not totally consistent on that. I'd like to use y. And in this case, my y initial would just be whatever the length of the string is. So we could write that out. M times g times L. And we are trying to solve for the velocity, the final velocity. So we just rearrange 1/2 mv final squared equals mgl. And the masses cancel. So a little more algebra gives us v final squared equals 2 times g times L. And v final is the square root of 2 times g times L. Or we might have called that h, like the initial height or something like that. We'll see an expression like this happening in many, many problems. V final equals the square root of 2 times g times the initial height. That's when something falls from a height h, it will go a speed vf given by this formula because of conservation of energy. So now we can put in our numbers. 2 square root of 2 times 9.8 times, now L is 75 centimeters, but I can't use centimeters if I don't want to have weird units. So I want to change that into 0.75 meters so that my units are all in the metric base unit, and that way I'm guaranteed I'm going to get something with meters per second for the velocity. So let's see what we get here. I get 3.83, and I know the units are meters per second because I was very careful to put everything into units with meters and seconds. That is, G had meters per second squared and L had meters. Okay, any questions? Haley.
I'm just confused how we went from the Y initial to the MGL. Is that like just because we know the length counts as Y initial?
Yeah, so what I have to do is I have to measure this distance right here. I have to measure that. That would be my Y initial. So because this string has a constant length, it's sort of moving like in a quarter of a circle. The radius of that circle is L. So that means this height must just be whatever the length of the string is.
Okay.
Okay, good. Other questions? All right. So let's try another problem. This one will combine a few things. So I want to talk about roller coasters because for two reasons. One, I just found out that Six Flags is open. That sounds kind of nuts to me, but I can't imagine they can make money because there can't be enough people. But at any rate, it's open. Anyone going to Six Flags this summer? Maybe it's not nuts. Raise your hand if you're going to Six Flags. Raise your hand if you would go if you got free tickets. One person. If one person would go if they got free tickets and that's it, that's not good for their business. Anyway, so we're going to talk about a roller coaster. The second reason is you guys have a new lab up called Energy Skate Park, and it involves, this kind of physics. And there's one part in it where I talk about making a loop-de-loop on a roller coaster. So let's just talk about how a roller coaster works. So basically, that's probably a little too steep there. So this thing kind of goes like this. You get on a cart. And the cart, there's a machine that kind of goes chick, 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 and it puts you up at the top of the roller coaster. And then it just lets you go, okay? And when it lets you go, what's happening is your potential energy becomes, as you go down, it's converted into kinetic energy. And the hope is that you have enough kinetic energy to keep you going around this loop, and then, you get back to the bottom. And so what we're going to do is we're going to work out the formula for the height, initial height, let's call it H initial, of a roller coaster. How tall does it have to be in order for us to go around a circular loop with a radius R? Okay, so how high does it have to be around the bottom, above the bottom of the loop? Does anyone have a guess how high it would have to be in order to make it around that loop? No? A lot of times people, Ziad?
100 feet.
100 feet? What if R is 300 feet?
For the radius?
Yeah.
I mean, I can't remember. I've been on roller coasters, but I can't remember how big they were.
Okay. Well, generally the height H is going to depend on how tall this loop is. Okay, so I'm really thinking in terms of R, how big does H initial have to be? And a lot of times people, if they're going to make a guess, they might guess that the height initial would have to be 2 times R. If it's not at least 2 times R, then we don't have enough juice to get us to the top. So we're going to find out that's not correct, but that's often what people would guess. Was anyone thinking that at all? Maybe if you were to guess, it might be 2R. Okay, yeah, it's a reasonable guess. It's a reasonable guess. That's a common thought about this. So let's see how this works. When we're going to assume there's no friction, of course there's really friction, which means that if you're building a roller coaster, this calculation that we're going to do would be sort of the minimum, but then you need to go even higher than that by some margin. We would say the net work equals the change in energy, but because it's frictionless, the only forces acting would be normal force, and the normal force is always perpendicular to the surface, and then there would be gravity. And gravity doesn't do work because, you know, we're kind of winking at each other and making this gentle person's agreement to pretend that it doesn't do work, because instead we are using this idea of potential energy, and the normal force doesn't do work because it's always at a angle to the path. So this looks very similar to the last problem. We get 0 equals KE final minus KE initial plus PE final minus PE initial. And I'm kind of measuring everything from the bottom of the loop-to-loop, okay? So in terms of potential energy, the initial potential energy, I'm definitely way above the bottom, so I have some of that. And the final potential energy, I'm really considering kind of this point. This to me is the critical place. I need to make it past here. And if I'm past here and I'm still on the track, then I'm in good shape. And at this point, I also have some potential energy. What about kinetic energy? So normally roller coasters do not give you a kick. They just get you up on the top and then they let you go. So your initial velocity would be 0. But you do not want to have 0 velocity here, because this is the last place you would want to run out. Okay, you would, you know, get here and then fall straight down. So we're going to have some kinetic energy at the end. Okay, so let's see what we have. We are going to have 1/2 m v final squared. So we're thinking of this point as initial and this point as final, plus m times g times y final minus m times g times y initial. I can see that the mass is going to cancel out of this problem because every single term has mass. So we can divide the whole equation by mass, and on the right-hand side it disappears. On the left-hand side, you know, 0 over mass is still just 0. So what am I looking for? I'm looking for the height initial, which would be my y initial. So we can move that to the other side. We have g times y initial equals g times y final plus 1/2 times v final squared. And the y initial is what I'm looking for, right? So y initial, if I divide both sides by g, would be y final plus v final squared over 2g. And let's get rid of y final. Y final, I know what it is. It's the diameter of this circle. That's just going to be 2 times r. Okay? So in fact, if the y initial were 2r, then in order for this to balance, we would have 0 velocity at the top, which would mean this would be the worst possible way to design it, because we get right to the top and then we stop there. But realistically, we probably get up here somewhere and then we kind of fall off of the track. That's what would really happen. Unless the cart is actually attached to the track case, we might just get stuck up there. Okay, so what remains is to find v final. We need to know how fast are we going at this point. And so for that, we need to rely on our circular, circular physics, centripetal force, centripetal acceleration. So when we're at this point, we're going to have, make that a little more vertical, we're going to have the force of gravity, and we will also have potentially a little bit of a normal force. And the normal force in this case points down because the track is actually above us. So it's like we're on the ceiling, and the normal force then points downward. So let's kind of make a little side calculation here, where we try to find how fast we have to go around this circle using centripetal force. So the net centripetal force is the force of gravity plus the normal force. And that's m times v squared over the radius of the track, capital R. Now we know force of gravity is m times g. And the normal force unfortunately, we don't have any way to find the normal force here. We don't have a way because we're already using the sum of the forces in the y direction, which happens to also be the centripetal direction. So let's see if we can figure out what to do with that normal force. So the idea is we are looking for how high this initial hill has to be to give us enough speed to make it around this circular loop. So we're really wanting the minimum speed possible that makes it around the loop to find the minimum height h. Of course, if we go higher than that, then the speed will be higher than the minimum speed necessary. But I'm looking kind of for that limiting, what's the smallest height h, which would correspond with the smallest speed that would make it around this track. So if I want the smallest speed v, that would go with the smallest normal force possible, and that normal force is 0. That's as small as the normal force can be. In other words, let me say this a different way. Why is the normal force 0? Because we're looking for the threshold when we're about to fall off of the track. And that's when we're barely in contact. It's just like a hair is touching, there's like a hair stuck to the wheel, and that's touching the track. Okay, so barely any contact with the track at all. Means the limit is when the normal force is essentially 0 because we're about to go airborne, but we just barely managed to stay on that track. Any questions about that normal force? So if the normal force is 0, then we can divide both sides by m and cancel out the m. And what we find out is that v squared would be equal to r times g. So that would be the final velocity that we had from the first part would be given by this formula. And so we have y initial equals 2r plus rg over 2g. We can see the g's cancel, and we have 2r plus r over 2. So that would be 2 1/2 times the radius. So for example, if r is 50 feet, then the y initial would have to be 125 feet. So that would be in this picture, 100 feet is the diameter, then we would need 125 feet for that initial hill. And you're going to hopefully see something like that in the lab if you haven't done that yet. All right, any questions about this problem? I know some of you were working on homework, and maybe one or two of the problems in the circular motion required you, without maybe you're realizing it, required you to use conservation of energy first to find the velocity. This one kind of goes the opposite way. We're using centripetal force to find the velocity, which we plug in, and knowing the final velocity allows us to know the height of the initial hill. But it's basically the same going in reverse. Grace?
How do we know when to use potential energy too? Because I know some of the homework you just use the kinetic one.
So if something is going up or downhill, then you're going to be either using work done by gravity or you're going to be using potential energy. And I would say you would only use work done by gravity if the problem specifically asks you to find work done by gravity. Otherwise, if something is going uphill, downhill in any way, then you're going to need to use potential energy.
Thank you.
Sure. Any other questions? Okay. So let's try another problem. using, let's see if we can get one that uses friction. Find the right problem. Okay, so this is problem 7.99 in the 3000 problems book. Okay, so it says a block of mass 3 kilograms starts from rest and slides down the surface, which corresponds to a quarter circle of 1.6 meter radius. So we have something like that, and we have only, only a quarter of the circle. And then we have a block sitting on this thing, and it's going to slide down, where the radius r is 1.6 meters. Now, it says if the curved surface is smooth, what is the speed at the bottom? So by saying smooth, they're implying no friction. Okay, that's what they're trying to imply. So in this case, this is the easy case, very similar to what we just did. I'm going to show you a shorthand way to streamline this process. We could use the following logic. We could say, okay, if there is no work done, no friction, then it must be the case that the initial energy equals the final energy. Okay, because there's nothing to change the energy. Initially, this thing only has potential energy. So, sorry, that's the final side. So I wanted that on the right-hand side. Initially, we only have potential energy, and the final energy is only kinetic energy. So you can think conceptually that what's happening here is we start a block with some potential energy, and as it slides down, that potential energy is completely converted into kinetic energy. So we have 1/2 mv final squared equals m times g times y initial. And like happens very often here, the mass is going to cancel out, and v final is going to be equal to the square root of 2 times g times y initial, which in this case, that would be 2 times 9.8 times 1.6. So that's that same pattern we saw before, the square root of 2 times g times the initial height. And the number for that looks like, I don't think I got that right. .6 meters per second. Okay, so the part A is not so interesting. It's pretty similar to what we've done, although it gives us an opportunity to kind of use logic. And I know some of you are a little more intuitive. You like to kind of work a little bit more intuitively, and this is a good intuitive way to think about it. But part B says, if the speed at the bottom is 4 meters per second, what is the energy dissipated by friction in the descent? So part B says, aha, but maybe we do this and we measure that V final equals only 4 meters per second. How much work done by friction was there? So, okay, we then say net work equals delta Ke plus delta Pe. And in this case, there would be work. That would be the work done by friction. And that we can open up these deltas to get Ke final minus Ke initial plus Pe final minus Pe initial. Okay, so now we go through these one by one, and we ask, what could be zero? Is the work done by friction zero? No, because that's what we're looking for. Is the final kinetic energy zero? No, they told us it's moving 4 meters per second. Is the initial kinetic energy zero? Yes, it is, because this is released. How about final potential energy? Well, we are allowed to call the bottom zero. So we make this decision that this equals, is y equals 0, and therefore we can call the final potential energy 0. But once we make that choice, the initial potential energy cannot be 0. Okay, so we have work done by friction equals 1/2 mv final squared minus m times g times y initial. Now, they gave us a mass of the block, which we didn't need for part A, but it's not going to cancel in part B because, there's a left-hand side here. So we can just plug in our numbers. We have 1/2 times 3 times 4 meters per second, and we square that, minus 3 times 9.8 times 1.6. And I get negative 23. Now the units of this, when there's work done, work is a transfer of energy, so the units would be joules. And then I want to go back to the problem and read the wording. It says, what is the energy dissipated by friction? So I would want to put this back into English and say 23 joules of energy dissipated. Okay, so the negative work means the energy is dissipated, and dissipated just means it's been converted into heat energy or some other kind of energy. It could be sound energy, the scraping sound as it scrapes down could be part of that energy. Okay. Any questions about part B? All right. Haley.
I'm sorry. So whenever we are doing the potential energy, that's the part you said that we can pick any location to make y equals 0. Is that for
Yes.
potential energy? Okay.
That's right. So I like to pick the bottom point in the problem, the lowest point, because intuitively that just makes the most sense. But we could just as easily pick the top and say this is y equals 0. Then what we would have had would be work friction equals 1/2 mv final squared. And what would happen is instead of canceling the final potential energy, we would cancel the initial. So it would be plus m times g times y final. But what would my y final be? It would be negative 1.6 meters. So that negative sign would be the same negative sign, that happened if I called the bottom 0, and then I took the potential energy initial instead of potential energy final. So we're going to get a minus sign one way or the other. Does that make sense?
Yeah, thank you.
Okay. Any other questions about part B before I move on to part C? So part C has, now we have this, this object moving, and it gets to the bottom, and it's moving at 4 meters per second. And now it's going to travel a distance of 3 meters before it stops. So that distance of 3 meters is also apparently rough, because otherwise this thing would just keep going forever. There must be some friction there. And the problem then says, what is, find the frictional force, and it's implying over this 3 meters. So let's capture a picture and move it on to another slide. And for part C, we can think of this as kind of a whole new problem, where the initial is kind of the bottom of the ramp and the final is the stopping point. And then we do conservation of energy all over again. Network equals delta KE plus delta PE. And in this case, there's still work, because this thing is going to lose energy and slow down. So this must be work done by friction. And that's going to be KE final minus KE initial. But look, this thing doesn't go uphill or downhill. So one step sooner, I could cross out delta PE and say, hey, the PE doesn't change anymore. So I can cross that out. So let's do that. The work friction then will be the friction force times delta X times the cosine of theta friction. And that's going to be equal to, well, KE final cancels out as well, because it comes to rest. So it's really just equal to minus 1/2 m v initial squared. Now, what is the theta friction? So to see theta friction, we need to draw our friction vector into the picture, or at least visualize it. And hopefully we can see that the angle between the delta x and the friction is 180 degrees. So I have friction times delta x times the cosine of 180 equals minus 1/2 m v initial squared. Cosine of 180 is itself minus 1. So the minus signs are going to cancel. And, you know, I want to be very careful. It says, find the frictional force. It does not ask us to find coefficient of friction. So let's find the frictional force, but then we can also find the coefficient of friction if we wanted to know it. If we only want the frictional force, F, then the F is just going to be m v initial squared over 2 times delta x. So what I'm doing is I'm canceling the minus signs. Cancel those minus signs. And then the 1/2, I'm just making it a 2 in the denominator, and we bring the delta x to the denominator also by dividing. So we divide by 2, and we divide by delta x. And that will be 3 times 4 squared over 2 times 3. And to save ourselves getting the calculator out, the 3's cancel. 4 squared is 16 divided by 2 gives us just 8. And 8 watts? It would be 8 newtons. If the problem, and some problems might do this, if it had asked instead to find mu, we could just say, the friction equals mu times the normal. In this case, the normal is just m times g because those are the only forces in the y direction. And so mu would be friction over mg. That is 8 over 3 times 9.8. That's 0.272. Again, that's not technically part of this problem, but if the problem wanted to know that instead, it's just one more step. All right, any questions about part C? Siad?
So I noticed that in the previous, in last night's homework, at one point they used cosine of 0 when I thought that they would use, cause it was basically like, they threw an object straight up, and for that one they used cosine of 0. So I wanted to know why maybe this is something I can ask after class, why they wouldn't use like 90 degrees, I guess.
Yeah, I mean, we'd have to look at that particular problem. So we can talk about that at some later time.
Sure, no problem.
Haley.
Okay, so I'm just confused. When we got the 180 for the cosine theta of f, is this the same like yesterday when we were saying you have to look? Because like, how is it not parallel to the displacement? Wouldn't that be like 0 then?
Well, but the friction points to the left and the displacement points to the right. So
Okay.
if you can imagine, if we put them both on the same place, the delta x points that way and the friction points this way. So the angle of delta x is 0 and the angle of friction is 180. And so if we would, that's going to be 180 degrees between those two vectors.
Okay, that makes sense.
So that's technically called, in math it sounds like it's parallel, but it's technically called anti-parallel because it's sort of parallel but going the opposite way. And that's when you get a 180 degree angle. Okay, other questions? Okay, this is probably a good time to take a break because we're going to learn about a new kind of energy next, and that takes a little while. So let's go ahead and take a 5-minute break.